Hello everyone, welcome to a video from my Algebra 2B class. This is for week 6, going over probability and counting principles. So for week 6, make sure you go into our assignments, use all your resources, do the paper pencil problems, use this video to help you understand all the different problems for the week. Here's what we got going on for week 6 with probability. If I give you a problem, we're going to be looking at how to take combinations of choices and use the fundamental counting principle to find the total number of ways to do something. We're going to recognize and learn how to count all the possible ways to do something if repetition is allowed, and in situations if repetition is not allowed. Finally, we're going to recognize when a problem involves permutations and use all the correct methods to count and identify all the possible permutations. And then we'll also look at combinations. So probability, counting methods, permutations, combinations. We got a lot to go over for this week. So we're taking a break. We're all done with algebra for a couple weeks. Again, in this throughout so far in Algebra 2, we've gone over linear functions, quadratic functions, polynomials, radicals. We just did a lot with rational expressions and rational functions. We're going to kind of mix it up and take a little bit of a break. We're going to spend 2 weeks looking at some fun and interesting probability problems and how to represent and solve them. So the kind of problems that we're going to get into, or we're going to potentially be able to look at throughout this week and next week, are how many locker combinations are possible for a school? What is the probability of winning the lottery? What are the odds of getting a full house in poker? How many license plates are there possible in the state of Oregon? And in how many ways can you choose a group of 4 out of a class? Because you guys are all going to start your scheduling pretty soon in the spring here. So these are all problems that involve probability, involve counting, and involve using some permutations and combinations to represent and figure these things out. So finding the probability of an event always involves finding all the possible ways to do something, and then finding all the possible ways that our specific event can happen. A really easy example is the probability of rolling 1 die and getting a 6. The probability is 1 out of 6 because there are 6 different ways to roll a die. I can get the numbers 1, 2, 3, 4, 5, or 6. Those are all the possible outcomes. But the one I want is the number 6. So there's 1 6 out of all 6 possible outcomes. So the probability is 1/6. So if we're doing probability and if we're getting more complicated than dice and jelly beans, we need to get really good at counting things and knowing how to count all the possible things. That's what we mean by counting principles. All right, here's a good problem to kickstart it off. At our school, we have 19 different math classes, 19 different ELA classes, language arts, 17 different science classes, 22 different social studies classes, and 75 different elective classes that high school students can take. If you need to take 1 math, 1 language arts, 1 science, 1 history, and 1 elective for spring, so you can sign up for 5 classes, how many different class schedules could you have? All right, let's start figuring out this problem. So one way, if we're looking at counting all the possible things, I like to use what's called a slot method. We have 5 different classes, right? I need to take 1 math. I need to take 1 ELA, language arts. Take 1 science class. I need to take 1 history. And I need to take 1 elective class. All right. That makes sense, right? 5 slots we have to fill and try and figure out all the possible ways. So now let's look at what our numbers are. In math, I have 19 different choices, right? So I need to pick 1 out of 19. Well, there's 19 total different math classes that I could choose. Just like when we rolled a dice, there were 6 different dice to choose. So here we got 19. For language arts, I've got 19 different choices. For science, we've got only 17. For history, we have 22. History, social studies, same thing. And for electives, we have 75. But I want to know all my schedules. So I can't just look at one independently. I have to take all 5 different categories and figure out how many potential ones. So I could pick one math class, but then I still have 19 other English language arts classes I could choose. Well, all the possibilities involve multiplying. And you probably have done this before using tree diagrams or thinking about if I have one and the other, all the different potential ways. But that's the fundamental counting principle. If we have all these different choices, we multiply all the choices to find out all the ways we can do something. All right, so let me get my calculator and let's actually figure this out. What is 19 times 19 times 17 times 22 times 75? Well, let me check that again. I got a super high number. 19 times 19 times 17 times 22 times 75. Okay, we have 10,126,050 different schedules that we could make. That's crazy, right? Over 10 million combinations, or 10 million different ways you could have a math, a language arts, a science, a history, an elective class here at Summit Learning Charter. All right, but there you go. That's counting all the possible ways. That's all the different schedules. So in general, the number of ways in which multiple events, that's just what we had multiple categories or multiple classes, but all the number of ways multiple events can occur can be determined by multiplying the number of possible outcomes for each event together. That's just what we did on the last one. We took each class, found all the possibilities, and multiplied them all together to find all the number of ways. What we did was the slot method. That was my personal favorite. It helps you just kind of see, make very visual all the stuff that you're counting. Let's keep looking at some more problems. You are asked to create a 4-digit PIN number for your ATM debit card. How many 4-digit PIN numbers are possible for you to pick from? Well, let's kind of think about this. Again, your debit card is a number when you slide your card. It asks you what's your PIN number. It helps give a little bit of security. So you could have the number 2309 would be a 4-digit PIN. You could have 1662. You could have 3456. You could have 888. Those are all possibilities, right? I just need a 4-digit PIN number for your ATM card. Well, let's use the slot method to figure this out. So we have 1, 2, 3, 4 different digits, right? And now how many choices? So for my first digit, I have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? There are 10 different digits that I could choose from. Now my second number, I can repeat, right? So I have the same 10 digits I could choose from, the same 10 digits for the third number, and the same 10 digits for the fourth number. If I multiply them all together, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. There are 10,000 potential different PIN numbers that you could have for your debit card. Which actually doesn't seem like that many, right? Everybody has a debit card. Everybody's got to pick a PIN. That's not all that many different PIN numbers. But now let's contrast this. Same problem, but there's one slight difference. You were asked to create a 4-digit PIN number for your ATM debit card. How many 4-digit PIN numbers are possible if you are not allowed to repeat numbers? Now this is a different problem, although it's really similar. So let's kind of take a look at this one. I still have 4 digits. I still want to choose a number. But now let's kind of go to this. Okay, so my first digit, I haven't chosen any yet. So there are all the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That are 10 different digits that I could choose my first one. Okay. But now I've chosen one of them. There's one digit that I can no longer use again. So now when I pick my second number, I have 0 through 9 except for the one I already chose. So there are only 9 numbers left to choose from. All right, so now I've picked 2 digits. So now when I get to my 3rd digit, there's 2 that I can't use. So there's only 8 left. And finally, on my last one, there's only 7 numbers left. I can't have any repeats. So if I pick a 1 for my first number, I can't use a 1 for my 2nd, 3rd, or 4th digits. So when you're looking at a problem, be careful if it says allowed to repeat or not allowed to repeat. It makes a big difference in how you represent it. So now let's multiply these together. And if I'm not allowed to repeat numbers, we got 10 times 9 times 8 times 7 equals 5,040. Look at that. It's almost half as many numbers if I'm not allowed to repeat. So there we go. Be careful of repeats as you're working with different types of counting problems. Okay, let's formalize our counting methods and start using some vocabulary here. We have this word in math called permutations, and the number of permutations of objects is the number of possible arrangements of the objects. So we're looking at arrangements and counting each of the different ones. That's a permutation. So here's a problem you would see. How many permutations are there of the 4 letters in the word math? All right, so we got 4 letters, right? Let's see if we can list them out. So math is 1 permutation. Now a different arrangement would be MA, but instead of TH, let's do HT. That's a different permutation, a different ordering of those 4 letters. Now let's do another one. Let's do T first. So THA and then MTAH. There's 2 more permutations. Let's do MA. We've got 2 A's, we have the 2 T's. Now let's do H first. HAT. And now we've got MHTA. All right, I think we've got all the permutations that start with M. So let's switch colors. And now let's start with H. So we have HAMT and HATM. Now we've got HTMA and HTAM. And then we've got HMAT and HMTA. Look at that, 6 more of them. That's kind of interesting. All right, let's keep moving on. Let's do blue. We started with M. We did the H's. Now let's start with the A's. A, M, T, A. Whoops, H, A, M, H, T. A, H, T, M. A, H, M, T. And then A, T, M, A. And ATAM. That's interesting. There's another 6 with the A's. You're probably already ahead of the game here, but yes, once I start with M, H, A, now I've got to start with T's. There's going to be 6 more with the T's. Let's just finish this off and just be really obvious about it. THMA, TAMH, TAHM, and the last 2 TMAH and TMHA. Those are 6 different permutations. Oh, sorry, not 6. Those are 24, 4, 8, 4 times 6. Those are 24 permutations. Different ways where I can take those 4 letters and rearrange them. Whew, that's a lot, right? Hopefully you get the good idea what a permutation is, however. A different arrangement. Every time I arrange something differently, it's a different permutation. So, again, another way to look at permutations, the order in which I have objects are arranged counts as a different permutation. For example, math and MHAT, those 4 are 2 different permutations, same 4 letters, but different permutations. Here's another permutation problem. If there are 9 players on a baseball team, how many different batting orders lineups can the coach create? Well, this is another permutation problem, but let's think about this. I can use the slot method for this problem as well too. So we've got 9 players, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to know how many different ways can I pick one guy to lead off, be the first batter, a different guy to be the second batter, and so on. Well, I've got 9 total players, so out of those 9 I can choose, there's 9 possible ones to choose for the first one. I pick one, then there's only 8 left, so there's 8 possibilities for the second one. 7, 6, 5, 4, 3, and 2. Once I've chosen the first 8, there's only one guy left, and he's just stuck being the last one. And if I use my multiplication counting principle, I can multiply all those together. And let's see what we get. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. There are 362,880 different batting lineups, different ways to choose someone, first, second, or third, or fourth, fifth, sixth, seventh, and eighth, and ninth, with just my 9 players. It's a great permutation problem. Okay, now you probably have noticed with the math thing, we had to draw those all out. It took a while. With the slot method, we listed them all out and it took a while to multiply them all. When working with permutations, mathematicians realized, wow, there's a lot of multiplication going on. So they created the factorial symbol. It looks like a little exclamation mark, but it helps, it's a sort of a shorthand representation of all this multiplication. So we did 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Well, we can represent that with what is called 9 factorial. That's equal to 9 factorial. That little exclamation mark means factorial, and it just means take whatever number you have and multiply by all the whole numbers below it. So if you have 5 factorial, if you see that, you're just going to do 5 times 4 times 3 times 2 times 1 and calculate what that equals. This one equals 120. Now, it may seem kind of pointless for small numbers like this, right? But what if you had 18 factorial or 42 factorial? You're not going to calculate all 42 numbers and multiply them, or all 18 numbers and multiply them. So we have a method in our calculator. So I'm going to switch gears here and show you where the factorial button is on your calculator so we can use it as you're working with problems. All right, here we are in our calculator. And I want to do that baseball problem, right? I want to calculate all the different ways I can have a batting lineup of 9 people. So that is 9 factorial, and I want to calculate that out. All right, so I got my keyboard up. I'm going to go to functions. And under functions, we're dealing a lot with statistics and probability. So I need to go up to the tab that says stats. And there you can see our n factorial. So you can go ahead and click it, and notice nothing's done yet because it's asking, well, what number do you want a factorial of? So I'm going to make 9 factorial. And there's the number we calculated, 362,880. It's calculating 9 times 8 times 7 times 6 for me, making it a little easier. What if we wanted to do 15 factorial? Let's go up. It's a big number, right? It's using scientific notation. So quickly multiplying grows very, very fast. And if we're getting anywhere above 8, 9, or 10 factorial, we're going to start getting very, very, very large numbers. But there you go. I wanted to show you where it was on the Desmos calculator. There's going to be some other probability and statistics calculation things coming up as well. So we'll come back to this here in a second. Let's go back to our PowerPoint. Okay, let's look at a slightly more complex permutation problem. At a track event, there are 12 students who are running the 800-meter race. How many different ways, again, that's a permutation problem, we're counting all the different ways, can one student finish first, another student second, and another third? All right, there's a couple ways to do this. I'm going to do one with the slot method, and then we'll do another one showing how to do this with permutations. All right, we have 3 spots, right? We want to know how many students finished first, second, and third. So that means I've got 12 or 3 slots. So I want to know how many different ways can we get a first, a second place, and a third place. But this time, I've got 12 students up here who are all possible choices, right? So let's think about this. So first place, somebody crosses the finish line. And I'm assuming everyone is an equal runner. I don't know anything about who's favored or who's faster or whatnot. But let's say it's completely random. So out of my first place, they're all running. There's 12 potentially different students that could win the race, right? Somebody wins out of those 12. So there's 12 different ways for someone to get first. Now one person's finished. They collapse in a heap. They're like dying. Whew, 800 meters, a hard race. But there's still 11 students running. So there's 11 students who are all trying to get second place. Some guy also finishes. And then we have 10 students left who are all fighting for third place. And someone from that group finally finishes as well. So how many different ways out of my 12 can we have a first, second, or third? Well, it is 12 times 11 times 10. So let's figure that out real quick here. 12 times 11 times 10 equals 1,320. So assuming completely random, that's how many different orders students can finish, or different outcomes potentially for winning the race. This one's a little bit different because I wasn't counting all 12 students. I didn't have 12 slots for 12 students. We only had 3 slots. So I only wanted to choose 3 students out of that 12, but it was still a permutation problem. Now, there's also a way to represent that same problem I just did using more of a formula, using factorial, and getting really formulaic in how I did that. So let's talk about what all these n's and r's and p's and everything mean. P means permutation. So this is a permutation problem. N means total number of things that we're counting. R is how many I choose. So out of that n, how many to choose? Sometimes I don't want all things. Sometimes I just want a small group, and I want to calculate how many permutations of a small group. So let's take our previous problem, right? Remember in the last one we just did, we had 12 students all running, so that would be my n. We are calculating how many different ways can the first 3 finish, first, second, and third, so 3 choices. And so according to my formula, I would set that up as possible. So the number of 12 students, I want to find the permutations of choosing 3, so how many different orders of first, second, and third. It's going to be equal to 12 factorial divided by, and n is 12, so we have 12 minus 3, r is 3, factorial. All right, now you wonder why we didn't calculate 12 factorial. We just did 12 times 11 times 10. The slot method seems so much easier, right? But this directly leads itself to the slot method because look at what we got. So 12 factorial is 12 times 11 times 10 times 9 times 8. I'm going to go ahead and patiently write all these out. All right, there's 12 factorial right there, right? But on the bottom, we have 12 minus 3, which is 9. We have 9 factorial. So I'm going to write out 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But look at what happens. Before I start just multiplying, we just did a whole bunch of factoring, right? What happens when I do this? Certain things divide out. Factors divide. 9 divided by 9 leaves 1. 8 divided by 8. 7 divided by 7. a lot of what's on the top and bottom factors out, so really it boils down to what is 12 times 11 times 10. That's exactly what we calculated in the previous problem. We did a slot method and we just got that, right? But this is more of a formulaic approach, and you can represent every permutation problem with this formula. How many are we choosing? And we divide out a certain number of them based on we only wanted to count 3, so we take the top 3. Everything else divides out. Now, your calculator, your Desmos calculator also has a permutation calculator built in. So let me show you where this is programmed in your Desmos calculator. All right, here we are. And we're going to do that same problem. We have 12 students running. How many different ways can we hit first, second, or third? So let's open up our keyboard. Let's go to functions. Now there is my NPR, just like we were calculating. So I'm going to go ahead and click it. This one looks a little bit different, right? It's asking me for some things inside of parentheses here. The first one is your N. So how many are we choosing from? Well, we had 12 students, so I'm going to put 12 in first, just like the N right there. So N first, 12 first. Now the permutations of how many things, how many choices of students did we want? We wanted to pick the top 3, so we put 3 in over there. And there it calculates that. There's our 12 times 11 times 10 right there, or 1,320. But there you go. You have your permutation calculator to check your work, make sure you're doing your math right as well. And it has this whole formula built into it. Okay, with permutations. Again, permutations are counting all the different arrangements of objects. The order in which we arrange them counts as a different permutation. But in math, sometimes we want to count combinations. In combinations, the order of the objects doesn't matter. I just want to count how many different groups. Let me try and distinguish between permutations and combinations here for a little bit. So permutations, math, M-A-T-H, H-A-T-M, and A-M-T-H were 3 different permutations, right? They're in different orders. So I would count that as 1, 2, and 3 different permutations. And if I kept going, we listed all of them, you got permutations. Now combinations, I'm looking as the group of a whole. What is in my group? And I don't care about the order. I want to think of all together. So M-A-T-H is this group of 4 letters. This right here is the same group of 4 letters. It's arranged differently, but it's still the same group. And so I have the same thing. Just like over here, AMTH is the same group of 4 letters. So all those are the same. And so really when I show that, that's only one combination of those 4 letters. So permutations, because we count all the different arrangements, we tend to count more permutations, and a combination problem tends to count less things because I'm only wanting to know in this group what is different from that group. Let's take a look a little bit more. So at Baskin Robbins and ice cream, here's a great combination problem. They always have 31 flavors of ice cream to choose from. You're very hungry, feeling like a sweet treat. You order a 3-scoop ice cream sundae with 3 different flavors of ice cream. How many different combinations are possible? Well, this is a combination problem because, let's see, here's my cup. If I choose chocolate ice cream, so there's chocolate, and I choose a scoop of vanilla, and I choose a scoop of strawberry, and then somebody else comes up and they choose vanilla. Maybe they choose vanilla first, and then they choose strawberry right here, and they choose chocolate. This is the same exact sundae, right? I'm walking away with the same bowl of the same scoops of ice cream. I don't really care like what's on top or side or whatever. It's the same thing. So it doesn't matter which I ordered and which they put the scoop in. I have the same bowl of 3-scoop ice cream. So for a different combination to be different, I would need to have chocolate, vanilla, And then over here, maybe like peanut butter. This is now a different combination. There's a different 3 scoops compared to that cup of 3 scoops. So combinations, again, the order doesn't matter. It has to be a different thing altogether. Okay. So now how do I start to calculate that then? Well, we can still use the slot method. So let's kind of write this down here. So I got 3 scoops I'm trying to get, right? 1, 2, 3. I'm looking at it carefully. There's 31 flavors to choose from, and it does specifically say 3 different flavors. So I can't just get vanilla, vanilla, vanilla. It has to be 3 different flavors. So out of my 31, there's 31 ways to pick the first scoop. There's only 30 left because I used a flavor. There's only 30 different flavors left for my second one, and there's only 29 flavors different from my third one. But now, this is my permutation right here, right? So if I multiply all that out, that gives me how many different orders. But now I need to figure out, well, how out of these 3, how many different ways are there the same? So now I have to think about, if I have 3 scoops, how many different orders do I have to keep track of, right? Strawberry, chocolate, vanilla is the same thing as chocolate, vanilla, strawberry. So I need to not overcount all the different same ones, even though they're different orders. So there's where I need to divide all the ways I'm counting the same combination. There were 3 scoops, right? So all the different ways of 3 things are 3 times 2 times 1. That's all the different ways. It's a permutation, right? How many different ways can I arrange 3 scoops of ice cream? 3 times 2 times 1 means there are 6 different ways to have the same thing. So I'm going to take 31 times 30 times 29. Let's calculate what that is. And 31 times 30 times 29. That is 26,970. So that's how many permutations there are, right? That's how many different ways I could pick 30 ice cream. But again, in my bowl, I don't care. I want to know how many different combinations. So I'm going to divide out all the ways I can have an arrangement of 3 things. I'm going to divide by 6. And then that'll leave me with how many combinations. So there's really only 4,495 different sundaes, different scoops, different groups of ice cream flavors that I can make. And that would be the answer to this problem. 4,495 different combinations of ice cream. If you had a bowl of 3 different types of scoops compared to someone else. Here's another way to kind of distinguish between combinations and permutations. A combination problem would say, how many ways are there to select the members of a committee from a larger population? So say we have a class of 30 students and I want a leadership team of 4 students, but they're a team. It doesn't matter the order. I just want a group of students. That would be a combination. A permutation would be, I have a group of 30 students and I want to pick a president, vice president, or a treasurer. That makes a difference, right? Picking someone for president is different than picking someone for vice president, so the order in which we pick matters. That's a permutation problem. A combination problem would be a way to set number of pizza toppings from a large list of choice. Again, if you order a pepperoni, sausage, and olive pizza, you don't care which one goes on first. You just want the pizza to have all 3 toppings. So different toppings would be combinations. But an ice cream problem would be ways to select and arrange scoops of ice cream. So if you wanted mint on the bottom and chocolate on top, that's different than if you really want chocolate on the bottom and mint on top. So permutations. Combinations, ways to select books from a reading list. There's 100 books and you say, I want to read these 4 over the summer. So you pick 4, that's your group of summer reading. That's different, that's a combination, as if you said permutations, ways to select and order. So I need to pick a book each month. So which one do I want to read September? Which one do I want to read October? Which one do I read February, etc.? That would be an ordering permutation problem. So it's all about, does the problem require a different order as a different thing, or are we just looking at one group and the ordering not matter? Again, there's your two formulas. So we looked at the permutation formula right here, right? N number of things, but we divide out a certain amount. The only difference between these two is in combinations, we do this extra division bit, just like we did before, where we divide out all the ways we have a different permutation. So if I'm choosing R number of things, all I need to divide by how many different ways I can do R number of things in a different order, because I don't care about the order. By the way, right next to on your calculator, where it had NPR on your Desmos calculator, there's also an NCR. So you can do combinations and permutations on your calculator as well as you're working through problems this week. All right, there we go. Week 6. That was good stuff, right? Hopefully you had some fun looking and thinking around with permutations, combinations, and counting all the different ways we can do something. Have fun working on the paper pencil problems, reading the textbook, and kind of just diving right into some interesting probability problems this week.